You tap a button on your screen to book a flight or hail a ride. It feels like a direct, private command sent to a single computer sitting in a server room. In the early days of personal computing, that mental model was closer to reality. Software was compute-intensive. The primary bottleneck was how fast a single CPU could crunch numbers. Today, processor speed is rarely the limiting factor. Most modern applications are data-intensive. Their success depends on managing the quantity of information, its complexity, and the speed at which it changes. Compressing a high-resolution video is a compute-intensive problem. You just need a faster processor. But searching millions of flight records and preventing two people from booking the same seat is a data-intensive challenge. Managing information at a global scale is the core problem of modern engineering. It requires moving and storing data reliably, even when the underlying hardware fails. A single, traditional database cannot satisfy all these requirements at once. The different ways we use data are simply too diverse. Most backends start with a primary database, known as the system of record. This is the authoritative source for every fact the application knows to be true. To speed up response times, engineers add a cache. This memory layer remembers the results of common requests and returns them instantly, saving the main database from unnecessary work. For complex queries, they use a search index. This specialized structure is designed for rapid keyword filtering, allowing the system to find specific terms without scanning the entire dataset. And to handle sudden traffic spikes, a message queue acts as a buffer. It holds tasks in a line, allowing the system to process them at a steady rate, instead of crashing under the load. Modern backends are composite data systems, carefully stitched together from these overlapping, specialized parts. Coordinating these different tools creates significant complexity. To keep the architecture stable, engineers measure every design decision against three specific pillars. First is reliability. Servers crash and networks drop, but a reliable system is resilient. It performs its expected function even when individual components fail. Next is scalability. When a social media user with millions of followers posts a message, that single update must be pushed to millions of timelines at once. This massive fan-out of data is a classic scaling bottleneck. Scalability is a system's capacity to add computing resources to handle a specific increase in load. Finally, there is maintainability. Engineering teams must design the system so that future developers can understand and evolve the software without breaking existing features. The job of a software architect is to manage the constant compromises between these three goals. No architecture is perfect. Every choice is a trade-off. Maximizing for absolute speed often requires sacrificing strong consistency. We can see these trade-offs by returning to that finger tapping a screen. This time, we'll look at the data architecture underneath the glass. When you browse for available dates, the request strikes the cache. The system returns pre-computed data instantly, protecting the main database from unnecessary load. But when you tap Reserve, the write request bypasses the cache, striking the system of record. The primary database locks that entry, ensuring no other user can book the same seat at the same time. Your confirmation is then pushed into a message queue. Background workers handle the email, while the app interface confirms your success immediately. When engineered correctly, the internet functions with the consistency of a natural resource. Alan Kay compared its scale and reliability to the Pacific Ocean, a man-made system that creates an illusion of effortless stability. That simplicity is an illusion. It only exists because engineers balance specialized tools against the inescapable laws of scale and failure.